Welcome back to another video with us here at LMDN STEM Academy. In this video, we will be working through the June 2018 Unit 1 Paper 2 question. It's a question 5, and it's centered around the topic of redox equilibria. So the first part asked, define the term standard electrode potential of a half cell. So the standard electrode potential of a half cell refers to the voltage measured under standard conditions with the standard hydrogen electrode as the other half cell. Okay? So now we're being asked to draw a labeled diagram to illustrate how the standard electrode potential of the Fe2 plus aqueous, Fe3 plus aqueous half cell can be measured. Okay? So in light of the definition that we just wrote, we know that if we need to find out the standard electrode potential of this half cell or other half cell, has to be the standard hydrogen electrode. Okay? And so conventionally, what we do typically is we draw the standard hydrogen electrode on the left. So I'm just going to draw my beaker here. And that would be my representative of my standard hydrogen electrode. That's what I'm putting on my left-hand side here. Standard hydrogen electrode. And you may see it in short, written as the SHE. That's your standard hydrogen electrode. And then, of course, the one that I want to measure the standard electrode potential for is this guy here. So I'm going to put that one on the right-hand side. And I'm going to put it in white. Okay, I'm going to put it in white. So here it is. Here is the beaker that will contain my solution. And that is for my, that's my Fe2 plus aqueous / Fe3 plus half cell. Okay, so that's what I'm going to put on the right-hand side here. Just conventionally, that's how you would do it. You would always put the SHE on the left. Okay, so that's one that we have here. All right, so let's fill it out now. So whenever we're drawing the standard hydrogen electrode, it has some unique features about it, right? The very first thing that we always have to include when we're drawing the SHE portion is we're gonna have our solution in it. So we have our solution in it, and that solution is gonna be an acid solution. So let me just write that solution that's in there is an acid solution containing it's gonna contain 1 mole, so 1.0. Let me just write that more clearly. That it will be a 1.0 mole per dm cube solution of H plus ion. So that's what that acid solution contains. That has to be the concentration of H plus ions in there. It has to be 1.0 mole per dm cube. And then what else do we want to say? Our electrode. Let's draw our electrode here. All right. I'm going to put the actual electrode now that's immersed into the fluid with a wire coming out. Right? That electrode right there is a platinum. It's made up of platinum, right? It's a PT electrode. That's what we're going to immerse in the solution. Okay? And then we generally draw like a little casing around it. Like this. And then around like this. And then in here, because remember, I know it's a SHE, so here's the source of the hydrogen gas. We're going to have hydrogen gas coming in up here. And it's going to be at, remember we're under standard conditions, so our temperature has to be standard temperature, 298 Kelvin, and the pressure of this gas would be 1 atmosphere. Okay? So those are the features of our hydrogen gas. It's coming in. We have a platinum electrode. We have our solution here. It's an acid solution containing 1 mole per dm cube of H plus. And then this closure that I drew here. So let me just make it balanced on that side. Bam, 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 bam. Let me just like do it like that. Okay, so this enclosure that we have is a glass tube. So let me just label it as such. Where should I label it? I'm gonna put the label in here. That's a glass tube with holes. So I'm gonna put the holes there to show you that glass tube that's around my setup here is a glass tube with holes to allow H2 gas to escape, okay? All right, so let me just put in some holes. So there's like a break here in the glass. So like perhaps here we have like a little break in it, and then the hydrogen gas now can escape from there. So those little bubbles there represent hydrogen gas, and it's the same thing over here. There's a little break in the glass, and we have hydrogen gas being able to escape out through there. And so we'll have some bubbling all throughout, right? And then they can escape through those holes that are in the glass tube. Okay. And then from a reaction standpoint, generally this is how we show what's happening at the SHE. It would be 2H plus aqueous plus 2E in equilibrium with the H2 gas. So that would be the half reaction that represents what's going on the hydrogen electrode. And generally, the standard electrode potential for the SHE is taken to be 0.00 volts. So we just take that to be 0. Okay, let me just make this clear. This is 0, guys. 0.00 volts. So that's the electrode potential, standard electrode potential of this hydrogen electrode. Now, remember our focus. Now, our focus was to find the standard electrode potential of this half cell. Okay? But we need to have this as well because that's what we're going to measure it against, right? And so let's come over here now and fill out this portion. All right? So what you will notice about this one that's unique and that's different than the one that we did in our previous video was that in this particular half cell, you see that there is no metal, like there's no metal portion of it. There's no solid portion of it. It's all just in aqueous form. And so when we draw that, right, this is how we're going to draw what's going on there is that in the solution, we're going to have our solution, of course, and that solution is going to have to be made up of, it's going to have Fe2 plus in the aqueous phase, and that's going to have to be a concentration again. Standard concentration is 1 mole per dm cube of that solution. We're going to need to have in here. And then we're also going to need to have Fe3 plus in there as well, right? Because it's a solution that's made up of both of those ions. And so again, standard concentration, it will have to be 1.0 mole per dm cube of that, right? So we have those two things in our solution, but we don't have anything, we don't have a metal form of it to act as the actual sheet or the electrode that gets dipped in there. And so again, we're gonna have to use our trusty PT electrode, okay? So PT is gonna be our electrode here. So it's gonna be a platinum electrode. Just as though we use a platinum electrode for the SHE, we're gonna use a PT electrode for this case as well, okay? Because it doesn't have a metal of its own to be dipped in it. So we use a PT electrode there. And then from here, it's just connecting them. It's just connecting the pieces, okay? So let me use a color for my connection line. I'm going to use a purple to connect them now, okay? So once this comes out here, it's going to connect to this other electrode wire. It's going to connect here, okay? So that's how we connect the two half cells. And then, of course, you know that we have to have our voltmeter in the middle, and that's what will give us the reading, right? So in here, we're going to have a voltmeter. It's going to need to be a high resistance voltmeter. So let's just jot that down here. High resistance voltmeter, and that will give us our voltmeter reading, which will be the standard electrical potential of this guy. So we need a high resistance voltmeter. So let's just label that real quickly. All right, so we have that high resistance voltmeter. That's going to be here. And then what do I have? I'm missing my salt bridge. So let's draw in our salt bridge for completeness sake. We need to have our salt bridge that's being dipped in both solutions. So that's my orange here. Here's my salt bridge. Bam, 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 bam. Okay, so that's my salt bridge. Okay, and we know what salt bridges are made up of. It's just a very strongly ionic solution. So we can do KNO3, we can use KCl, or you can use NaCl. So any of those guys could be in your salt bridge. NaCl, so sodium chloride, okay? And so, yeah, we've captured everything here that's needed to measure the standard electrode potential of this half cell. So whatever our voltmeter reads, once we've connected everything to the SHE, then that value will be what it is for the Fe2 plus, Fe3 plus half cell. So the value that you would see in your table for the Fe3 plus, Fe2 plus half cell would have been measured using this approach, right? And so what was that? Let's see what that value is. That value from if you look in your table, you would see that in your data booklet, you would see that Fe3 plus aqueous plus equilibrium, Fe2 plus aqueous. If you looked in the data table, it would show you a standard electrode potential for that collection of ions together. It would show you a value of positive 0.77 volts. Okay, and so whenever you do this is the setup that you would use to determine this value. Okay, so that's how you would set it up. And so with that, let's move on to the other part of this question. And so the other part of this question now is saying, state two uses of the standard electrode potential. So once you've gotten a standard electrode potential for a particular half cell of your liking, whichever one, there are two ways that you can use it. So we're going to state two of those ways here. The first way is to figure out the relative oxidizing and reducing powers of metals, right? And so generally, we know that the relative oxidizing and reducing power. So which one is a really good oxidizing agent? Good oxidizing agent have a more positive standard cell potential, standard electrode potential rather, if it's a good oxidizing agent. And if it's a good reducing agent, then it would have a more negative value, okay? So that's just something that we know based on our prior knowledge. And so if I'm comparing two metals and one has a more positive standard electrode potential and one has a more negative one, then I'll know that this one would do a better job at behaving like a reducing agent. And this one would do a better job at behaving like an oxidizing agent, right? Remember, oxidizing agents, they want to get reduced. And so they have a more positive standard electrode potential. And the reducing agents, they want to be oxidized, and so they have a more negative standard electrode potential. So keep that in mind. But the long and short of it is that we can use standard electrode potential to figure out the relative oxidizing and reducing powers of metals. And then also, very, very importantly, we can use the standard electrode potential values of half cells to assess the feasibility of a chemical reaction. So I can use the whatever I have for one and the other, and when I add those together, I can determine if it's feasible for those two things to come together. Feasible just means, is it possible that they can react together? Okay? And so those are two ways that we can use the standard electrode potential. Now, let's move on. So the other part is telling us, okay, now let's consider a cell that's represented below. Consider this cell, right? So here we're seeing our cell diagram, and we spoke about in the earlier video how to break this apart. So how to understand what's really going on here, right? So when we look at what's on the left will tell us what our anode is. So the reaction that's happening at the anode will be represented by this. We know that this is our salt bridge. We said that earlier, that those two vertical lines represent our salt bridge. And we said that whatever is to the right of that is what's going on at our cathode. Okay? The reduction that's going on at our cathode. So that's what the cell, that's what the cell says in a nutshell. Okay? So let's see what else is being asked of us now, specifically related to this representation. So we're being asked to write the equation for the reaction between copper and silver ions, okay? So that's a full reaction that they're asking us to put together. But let's start by writing out the halves. Let's write out the anode half, and let's write out the cathode half, and then finally put it together to get the full thing. They want the full thing, okay? So let's write the halves first. So at my anode, right, at my anode half, I'm gonna have the copper solid that is being oxidized to Cu2 plus aqueous. That's what's going on at my anode, oxidation. Okay, so that guy would have lost, the solid would have lost 2 electrons to get to this form. So that's at my anode. At my cathode, I'm gonna have reduction. So my silver ion, which is Ag plus, in its aqueous phase, is gonna get reduced. So that means that it's gonna gain an electron to then become solid silver. Okay? So that's what's going on at my cathode. Now, if I'm gonna come up with a full equation, like a full equation for the reaction, I'm gonna have to make sure that my charges are balanced. And so when I look at the anode, I see that the copper is losing 2 electrons, but the silver at the cathode is only gaining 1. But remember now, you see, whatever the anode loses, that's what the cathode has to gain, because that's where the electrons are coming from. So if the anode is losing 2, then the cathode has to be gaining 2. And so to balance that, we're going to just multiply the cathode reaction by 2. And so that way we're going to end up with 2 moles of Ag ions in the aqueous phase plus the 2 electrons that it's gaining from the anode, right? And then we're going to have 2 moles of Ag solid. So I multiply through everything by the 2. Okay? Multiply through everything by the 2 to get this. So this is my final representation of what's happening at my cathode, right? So this is the final one. Final for what's going on at the cathode. So final for what's going on at the cathode once I've balanced my charges. And so if I need to get my overall, then I'm going to need to add this to this. So let's write what's happening at the anode. Let's call that equation 1, and let's call this equation 2. So then I'm going to have to add everything together to get the overall reaction for the copper and the silver ions reacting together. So when I'm adding equations, I'm going to take what's on my reactant side in both cases. So that's copper solid. So I'm going to write my copper solid first. And then I'm going to take my reactant from down here, which will be the 2 Ag plus in the aqueous phase. And then That's going to get equilibrated with the Cu2 plus that's over here on the product side. So now I'm on my product side. And then down here on the product side for this one from equation 2 was the 2 moles of silver. So I'll just put that right here in the solid phase. Now the electrons went away. They actually canceled out each other, right? Because they're on opposite sides. So my electrons at the anode are over here on the right, and my 2 electrons at the cathode are over here on the left. So they canceled out. And so that's why my final form of the reaction, which is my answer, which is what they want, doesn't show any electrons in there, okay? Because they all canceled out. You lost the 2 and this guy gained the 2 in order to become what it ended up becoming, right? And so our final answer then for that equation would be just this, okay? But that's how you would arrive at the equation, is that you'd have to write both halves, balance the charges, and then add them together, and that's what you'd end up with. Okay, and that's our final answer here. So let me just clear everything here. And so that's our final answer that we just got. Okay, and so let's move along right now. So now we're being asked to consider the same cell, and we're being asked to calculate the standard cell potential, right? The standard cell potential from a formula standpoint can be represented as the standard electrode potential at the cathode minus the standard electrode potential at the anode. So remember, over here was our anode, right? And this was our cathode, right? And so at this point, you'd have to look in your table, your data booklet, and you're going to have to find what the standard electrode potential for this half cell is. And you're going to have to look what it is for this one as well. When I went to my data booklet, I found that for this particular half cell, the standard electrode potential was positive 0.80 volt. And for this particular anode, the standard electrode potential was 0.34. And so applying this formula here to calculate the standard cell potential, I just plugged in the 0.80 here, and then I plugged in the 0.34 here for the anode, and then I came out with a value of positive 0.46 volts, okay? So that's my standard cell potential for this pair in here. It's positive 0.46 volts. So let's keep that number in mind, okay? All right, so let's clear this and move on. And so now we're being asked to assess the feasibility of the reaction. So can this copper ion really react with the silver ion as we wrote it earlier in the reaction form? Is that really possible? That's what they're asking us. And so that's what feasibility means. And so for a reaction to be feasible, the standard cell potential must be positive. It must be positive in value, okay? And since the value for the standard cell potential in B part 2 that we just found, we found it to actually be what? We found it to be positive 0.46 volts, right? That was our E standard for the cell. That's what we had gotten. So because we got that to be a positive number, this means that the reaction between copper and silver ions is in fact feasible. Okay? All right, so moving right along now, let's see what else there is. We're being asked to assess the effect of an increase in the concentration of silver ions on the standard cell potential. All right, so let's bring up back our equation here that we came up with. So this is our equation for what's going on with the silver ions reacting with the copper. This is our equation, right? So when we think about the increase in concentration of silver ions, effectively what we're doing is we're sending this one up. We're increasing this. So if we have to think about what's going to happen, then we can rely on our knowledge of Le Chatelier's principle, right? Because effectively what we're doing is we're imposing a change on this equilibrium, right? This is an equilibrium that's established. And so if I increase the concentration of silver ions, the system has to push back to oppose that change, right? And the way it opposes that change is that if I increase the concentration of silver ions, the equilibrium has to shift to the right, right? The equilibrium has to shift over here, right? So think of what's happening when we're shifting to the right. When we're shifting to the right, more Ag plus ions are getting reduced, right? So that means that more electrons are being consumed, right? Reduction is the gain of electrons. So these new guys that I dumped in, these new silver ions, have to gain electrons. And if you're gaining electrons and depleting electrons from the solution, the net effect is that the standard cell potential will become more positive. Okay? So that's the net result. The standard cell potential will become more positive because you're depleting electrons to use up this extra amount of AgCl that got added in. So if you're devoid of electrons, you're using up electrons, you're becoming more positive. Okay, you're taking away those negative charges, and so you're becoming more positive. So if I were to write this out, how would I write on the exam? I would write that increasing the concentration of silver ions will result in an increase in the standard cell potential. This is because the equilibrium position will shift to the right as more electrons are going to be accepted by the silver ions that I added in. And so when electrons are more easily accepted, the value of the standard cell potential gets more positive. Okay? So that's our answer here. And so with that, we've come to the end of this question. Consider subscribing to the channel. And if you look here, right, on your left, you will see the next video up. If you look on your right, you will see the Module 2 playlist, where there are tons of other content for you to indulge in and get yourself ready for this exam, okay? Thanks for watching, and see you in our next video.